Hello, this is section 1.3. We're going to be talking about continuity, end behavior, and the limits of our functions. There are three different types of discontinuity we're going to talk about. The first is infinite, and that is where we have our graph and we have a function that heads off in one direction, and then there's a point at which it starts up and heads off from another. Okay? At that line, the function has no value, and that's considered a point is discontinuous. And that discontinuousness is infinite in how far apart the last point is on one side of the line to the first point on the other side. Okay? So they're nowhere near each other. They're total opposite ends of the number line spectrum. They're not always that way though. Sometimes it's simply a jump where you have two functions or maybe a piecewise function, and you have at some given point you have the function on the left coming to a point and stopping, and the next function starting up at that same point but in a different location. So we've simply jumped a gap, not a total infinite distance. And then the third is where we had our functions that would have a hole in them, and we call those removable. Where we have our line, and because it was a fraction, there was one point in the denominator that was not a part of the function. And so we had a hole. That hole was simply removable. Okay? Whether a function is continuous or not depends on a few factors, and we call this a continuity test. For our continuity test, one, our function has to be defined at the point we're looking at to see if at a certain point, whether or not it's continuous. There's a few things we need to look at. The first is the function, f of x, is it defined at the point? And we're going to call the point C. So I'm going to refer to it as f of x defined at point C, or where we evaluate function f at C. Okay? The second test is, does the function approach the same value from either side? Okay? And the third is the limit. So as it's approaching that same value from either side, is that side actually a value of the function at point C? So we refer to that as, is the limit as x approaches C of x, is that the actual value of the function at point C? Okay? So for our continuity tests, these three functions were not continuous. The first one did not have a defined value at point C, and so you don't even need the other two, but the limits are the opposite, so they weren't the same for number 3, and it's not approaching the same point. Okay? For the jump, it is defined at point C, we have a value, but it's not approaching the same value from either side. It's approaching two different locations. And therefore, the limit for this one is approaching here, but its value is actually here. So it doesn't match 2 or 3. For the removable, it is not defined at point C. It is approaching point C from both sides, and the limit's that point, but it doesn't have an actual value there. Okay? So if we look at these factors, and we look at some examples. Number 1, f of x is 2x squared minus 3x minus 1. Question is it continuous at x equals 2? Okay? And we can look at a graph of this function. And the graph of this function looks like this. Okay? So at 2, it has a defined value. It is approaching that same point from either side, and the limit that it's approaching is that point. So for a quadratic or a line with no gaps or anything, our answer, if it's continuous, is yes. If we have a piecewise function, it's hard to say. We got to look at it. So if we have f of x is 1 over x if x is less than 0, and x if x is greater than or equal to 0. And the point where we're going to be questioning it, of course, is going to be at 0, where we change functions. Is this continuous at x equals 0? And what we find is that it's not. Because as we approach 0 and the numbers get really, really small up here, we get a very large number. It's heading off towards infinity. Okay? But when we start y equals x, that starts right at 0. So the numbers near each other. So if we were to look at a graph, for the second one, where x is greater than 0 and equal, we're starting right here, and we've got the y equals x line heading up and out. But on this side, for the fraction, if you think about it, we're starting at, if we're at 2, we're at like 1/2. And so it actually starts here hugging the axis, and then it hugs and goes up the axis like this, never to touch. And so the point here right next to 0 is at infinity, and then the next point is at 0. There is an infinite disconnect. And even though it's only in one side, it's still infinite because it is infinite all the way up here back to this point. Okay, it's not necessarily a jump. Okay, so the answer for this one is no. If we look at a third example, and we have f of x and we have 3x minus 2, which is a line, and we have 2 minus x, which is also a line, and the top one goes from x is less than negative 3, and the bottom is x is greater than or equal to negative 3. Is this continuous at negative 3? It's going to be a negative 9 minus 2 is a negative 11, and negative 2 minus a negative 3 would be a positive 1. So there's a jump. So it's not going to be continuous. But the question I'm going to ask you, though, is identify a point of discontinuity. Okay? And the point of discontinuity is where we change functions. Because this is going to be a nice solid line until we get to negative 3. And this is going to be a nice solid line from negative 3 on. But the point at which we change functions is going to be our point of discontinuity. So the point is at x equals negative 3. That's where we change from one function to the other, and the function is no longer continuous. The last thing you're going to be asked to do is to identify zeros, or approximate zeros. Now, with Desmos, we can plug in a graph and get the zero very easily. You can just trace it around and, oh look, there it is. But prior to graphing calculators, we would try to approximate them, okay? And we would graph a function out and give an approximation. So when they ask you for the approximate zero, they're asking you, well, between what points is the zero at? Okay? If we look at this function over the domain negative 4 to 4, and they want us to find where those approximate zeros are. Okay? Well, this function over that domain looks like this. Negative 4 to 4. And the function goes up like that, and then it comes back down here, and then it goes back up like that. Okay? And to look at our approximate zeros, we're going to be between negative 2 and negative 1. Oh, sorry. I have this in the wrong spot. It should be going like this. So it should be between negative 3, you type it in the graphing calculator, and negative 2. We will have another one between 0 and 1. And we'll have another one between 1 and 2. Those are the three areas where we have a zero to the graph, or it crosses the x-axis. Okay? That's it for section 1.3 on continuity and behavior and limits. There's only one video this time. Look forward to seeing you in 1.4.